Greetings, folks. Welcome to the latest edition of Conceptual Astrophysics. This is a series of videos in which we show how to set up and solve introductory astronomy problems. I am your host, Dr. Christopher Sorolla. Today we're taking a look at apparent sizes, specifically angular sizes. This is how astronomers talk about how something appears to be in the sky by angles. And we're using as an example the moon. Specifically, you might have noticed this, that the moon sometimes looks bigger than it does at other times. Now, this is not to talk about the phases of the moon. That's a completely different question. Let's compare like to like. So let's compare, say, the size of the full moon to the size of the full moon at some other date when it looks to be a different size. And why would the moon look to be a different size? The moon doesn't grow or shrink, of course. That means it must be different distances away. And the way in which we talk about that is by angles. So how large does the moon appear to be across the sky is an angle idea, right? So let's talk about the following. Moon's diameter is some 3,476 kilometers, and its orbit is elliptical, which means sometimes it's closer to the Earth, sometimes it's further away. At its closest approach is 362,900 kilometers from us, and the furthest it ever gets from the Earth is 405,100 kilometers. How much larger does a full moon appear when it's closest compared to when it's at its furthest distance? And how would we go about talking about this? Okay, so to do a problem like this, it often helps to set up a table or a list of known and unknown things. So let's do that. Let's explicitly write this out. And this is a good approach, especially when you're beginning problems, because it allows us to see exactly what's in front of us. And it helps us understand better how to read a problem. So, for example, the moon's diameter is this number of kilometers. Now, let's use a capital D to stand for diameter. That's pretty common. And so 3,476 km for kilometers. So there's the diameter of the moon, all right? Now, that's a specific thing, right? The moon's not changing size, so that number doesn't change. But its distance from us does change because of its orbit. Now, in the problem write-up, it also talks about this. The closest approach to the moon is called perigee. Now, para is a prefix that means close, and G is in geo, like geology, geography, meaning Earth. So closest to Earth is literally what perigee stands for. And the way that astronomers abbreviate perigee is with the PE. So let's write PE for the perigee distance, and its closest approach is this number of kilometers here. So 362,900 kilometers, like that. All right. Now, the other idea, the other end of the moon's orbit, if you will, is called the apogee. And again, ap is a prefix that means furthest, and G, Earth, so apogee, furthest from the Earth. Same kind of idea, except opposite in what we're doing. We'll use AP, ap, to abbreviate this distance, the apogee distance. And again, the problem states it's this number of kilometers. Okay. So these are the known ideas, all right? Now, what are we trying to figure out for the unknowns, right? Well, unknown, first off, what is the angle at perigee? And what is the angular size of the moon at apogee? Now, for starters, let's take a look at this weird symbol here. This, in case you haven't seen this or aren't familiar with it before, is the Greek letter theta, or theta, if you will. It's their letter for the sound TH. We don't have an individual letter for the sound TH, but that's not a big deal. And this is a very common symbol used to represent angles. So you may have seen this in math classes or other science type classes before. And it's very common to do so here. Okay, so that's one thing. Second thing is, let's sketch a quick picture here to represent what exactly we're talking about. So let's imagine we have the moon here, and here we are on Earth, the observers, like this. So if you're wondering what that little thing is, that's a little stylized eyeball. It's not meant to be creepy. I apologize if it is. What it's meant to illustrate is an observer, whether it's you or me or a telescope, an instrument, that kind of thing. And what we're talking about is the angular size as seen from us, the observer. So how would we illustrate that? Well, let's sketch out a picture. So I can draw a couple of straight lines starting from us, the observer, and going past the edges of the moon like that. And that is going to give us a fairly good feel for what we mean by this angle. So the angle we're talking about in general terms is right in here, okay? Now, what else do we know about this problem, or what we have? This distance from here to here is the physical diameter, capital D, like that. And then the distance from the observer to the moon we'll symbolize with a little letter d for the moment. I'm going to give that something to play with. And I can sketch that out as so. So go from here, say, to here like this. And I'll call it little d for distance in general. Now, I'm not calling it little d in general over here because these are specific things, right? So when we get to actually doing our calculations, we're going to use specific numbers. But little d is a distance in general. Okay, so keep that straight. We got two d words, unfortunately. D for distance, d for diameter. How do we keep them straight? Capital D is diameter, little letter d is distance. And that's a pretty common usage. All right, so how do I relate all these various things together? Well, we're going to go off a little bit into trigonometry, not much. And I'm not going to give you a big long lesson or anything, just simply state a result. You might be familiar with trig, that there are several different things or functions that relate the sides of triangles. And one of those is called the tangent. Now the tangent is defined as the opposite side divided by the adjacent side. And if you look, we sort of have that going on here. We have a side that's opposite the angle. So the angle's here, opposite that, there's a side. And then here's this straight line length that will stand for our adjacent side. And so tangent of our angle, TAN, short for tangent, equals the opposite side, capital D, divided by the adjacent side, little d, looks like that. One more bit. We're not interested in the tangent as such. We're interested in the angle itself, right? So what you want to do is invert or do an inverse function, if you will, on all of this to get the angle itself. So the angle will be what we call the inverse tangent, which is symbolized like this, and then of this ratio. Now, this is something to watch out for. If your calculator is already set to units of degrees, you're good to go. We'll leave it like that. Some calculators, especially Texas Instruments, tend to reset or always have a default setting in units called radians. That is a useful unit, but not for us today. We're not using that today. So to make sure that your calculations come out correctly, you want to make sure that your calculator is set to degree mode, not radian mode. So we don't want radians, we want degrees. This is also true for an average cell phone. Cell phones tend to have the default set at degrees, but there is also an option to choose for radians. Again, we don't want radians, we want degrees for our purposes here. Okay, and it's not, in the long run, it wouldn't matter too much, but degrees are a little bit easier to handle, so we'll stick with degrees. Okay, so with that in mind, let's solve for the angles at perigee and apogee. So this is a general formula. We want to take that general formula and apply specifics to it. So we're interested in the perigee angle, for example. That would be the inverse tangent of the diameter of the moon divided by the perigee distance, like this. Okay. Now, I don't have to have anything different for diameter because the moon's always the same size and shape, right? It doesn't change. But the perigee is a specific thing, so we have to use that specific number. And I'm going to use a little subscript here, PE, on my angle to denote that, to distinguish it from other angles. Something else about a calculator, typically, and again, this will show up on an average scientific calculator or a cell phone calculator, TAN with a -1 as a little label right behind it like that, that stands for the inverse function. So you invert or undo the tangent, if you will. That's what you're looking for. So a lot of calculators, you'll have to push a second function key to access it. But there it is. All right, so let's do an inverse tangent of this ratio of numbers. So capital D, 3476 kilometers, like that. PE is this number, 362,900 kilometers. like this, okay? So divide this number by that number, okay? Now, one thing also to note, the units are kilometers, both top and bottom, and kilometers divided by kilometers cancels out. Or if you prefer, kilometers divided by kilometers is 1, and 1 multiplied by anything doesn't change your answer, so it goes away. I say this in part because you want to make sure when you're doing calculations of this sort, say angle-related calculations, you want these two values to be in the same set of units. If I have my units, say, described over here in miles, which for the moon, for example, would be about 2,000 miles, and then divide by this number, which is in kilometers, I'm not going to get the correct response. So always make sure that your units are in agreement with each other, and that's what we've done here. Okay. Long story short, let's go find our perigee angle, and if I crunch the numbers into my calculator, I get 0.549 degrees. So a little over half a degree across, okay? So when you look at the full moon up in the sky, the moon is roughly half a degree across. Now, how does it change, or how is it different if we look at the moon when it's at apogee? So same calculation, except subscript AP for apogee angle now. And this will be inverse tangent of the diameter. Again, diameter is the same in all cases, so that doesn't change. But now it's the apogee distance. So notice how that works. Again, 3476 kilometers in the numerator, or the top, if you will. Apogee distance is 45100, so that's the number I use here, like that. And in the case of apogee, just to shorten this up a little bit, I get 0.492 degrees. All right, so this is kind of interesting. The moon is, well, it's not super smaller or super different in terms of its size, but it is something you might notice. And to get you a feel for that, let's sketch out, say, distances to give an idea. Now, I'm not going to try to draw a full circle, say, to stand for the moon, but let's do this kind of trick. Let's sketch out the length, or say the diameter, of the moon at apogee to scale with the diameter of the moon at perigee. So if I start here, let's suppose instead of 0.492 degrees, I had 4.92, say, centimeters. All right, so 1, 2, 3, 4.92, right about there. So this would be the diameter, the apparent diameter of the moon, or the apparent angle of the moon at apogee, right? Now, what is that going to be in comparison to, say, the moon at perigee? Same idea. Let's line it up so we have a fair comparison. But now, instead of going 4.92, I go 5.49. So let's do that. So 5.49, almost 5.5. And check out the difference. The moon is a little bit bigger at perigee, appears, I should say. It isn't actually bigger, right? It appears to be bigger at perigee compared to its size at apogee. Now, one more trick to do, or one more set of tricks to do, to get a fair comparison, let's take a ratio of these apparent sizes. So let's do a ratio. How big is the moon at, say, perigee compared to apogee? So angle at perigee divided by angle at apogee, like this. This will give us some kind of idea as to how big the moon is across compared to it. So 0.549 degrees compared to 0.492 degrees, like this. And you always should check the calculations to make sure I did my calculations correctly, but assuming I did, I'll go ahead and write down my answer, 1.16 times. So the moon looks 1.16 times larger across at perigee than it does at apogee. One more trick, though, one more thing that might help us understand what's going on. Well, see, the moon isn't a line, right? The moon is actually a full disk at full moon, isn't it? And so we should really ask ourselves, how much bigger is the full moon as a disk at perigee compared to apogee? And that's an area idea. How much area does the moon cover, right? So let's do that. Let's take this ratio and square it. So the area ratio, if you will. Now, why am I going to square it? Well, the moon is a disk, or it looks like a disk, And the formula for the area of a disk is pi r squared, if you remember. Pi times the radius squared, or related to the square of the diameter. So let's take this number, 1.16, and square it. And that number then turns out to be 1.25. Now, why is that an interesting result? Check it out. The moon then is 25% brighter at perigee than at apogee. That's what that means. That's significant. That's enough that you can tell the difference. Now, problem with all this, in a sense, is that, of course, you don't have the comparisons of them side by side, right? So one month you might see the moon at perigee, some other month during the year you'll see it close to apogee, and you'll have to sort of remember how big it looks. Or what you could do is take a picture of the moon to scale at, say, perigee. When it comes close to apogee and full moon, take another picture like that, and then you could, say, line the pictures up and compare them. That's been done. You could go online and see these kinds of things, and it is significantly larger. So now, this is, by the way, not the same thing as talking about special effects like, say, the optical illusions you get when the moon is close to the horizon. That's a whole different discussion. This is straight up, imagine the moon's very high up in the sky, look at the moon at apogee, look at the moon at perigee, we compare the two. And the moon is much bigger, well, not much, but larger enough at this perigee distance that you can tell that there's something is going on. What is that something? That something is the moon's elliptical orbit. All right, thank you everybody for your attention. This is Conceptual Astrophysics. I was your host, Dr. Chris Sorolla, thanking everybody for your attention and clear skies.